Hello, my name is Tan Tang Wu. So this that we were assigned to conduct the experiment. The topic is where force vibration system with single degree of freedom. So we will carry out these experiments by using the material and equipment provided by this lab. So that is the spin mass spin, the rotating auto speed control, also the EAQ software and hardware, and also the sensors that is thermometer and accelerometer. So we will use the spin mass system as a model of a real engineering system. The spin mass can be thought of as representing a single mode of vibration in a real system like the bridge response, where natural frequency and damping coefficient coincide with our spin mass system. So it's important to calculate the natural frequency, as if the excitation frequency coincident with it, it would break the system or the bridge in the real life. Thus, in this experiment, we decided to calculate the natural frequency of this system as well as the decay rate. Besides, we also determine the system is under damped system or others.
Hello, my name is Lukman and I will brief you about the experiment setup. Okay, this is the tachometer. We use this device to measure the rotational speed of the motor. And then we have the measurement instrument which convert the analog input from tachometer and accelerometer into digital input through the Digilab software. Then we have also the rod that control the speed of the motor. And last but not least, we have this accelerometer which used to divide to measure the vibration that happen through the experiment in this beam. Thank you.
Hey guys, for those who don't know me, my name is Taiyan. Now I'm going to show to you how to obtain the signal by using NIDAQ software and synchronize it by using BaseLab. Come on. First, open the NIDAQ software, open the data neighborhood, select the acceleration, select the channel 0, change the name, next, change the sensitivity to 106. Change the mode to continuous sample. Add the voltage from channel 3. Click run. Wait for a while. Click stop and save. Next, open the Digilab. Import the analog input. After import the analog input, click measurement from the hardware setup, synchronize it. Next, choose the time-based setting, select the task name, next, double click the analog input, select the task name, and click OK. So this is the module of our system.
Hey guys, for those who don't know me, my name is Sifan. So today I would like to demonstrate to you on how to obtain the data for natural frequency and decay rate. First, you will need a timer, and then make sure your motor is not moving. Then we will increase the speed of the motor every 10 seconds. After the speed has reached the maximum, we will wait for 10 seconds and then stop it immediately. Okay, now I will show you.
So after we obtain the graph, we will enlarge the window, then show the cursor, and then zoom the part that has the highest peak. Put the cursor at the two highest peak, like this. Then the frequency here will be the damping frequency, and it will then proceed with manual calculation for the natural frequency.
Okay, done with the natural frequency. Now I would like to show you on how to obtain the data for decay rate. First, make sure your motor is not moving, and then I will apply the force like this. And the data will be shown in the daisy lab.
So this will be the graph that we obtain after the load is applied. Then we will show the survey and the cursor. Next, zoom the part which is showing decaying. Yeah, here, and then put the cursor at the first peak and the second cursor at the next peak. Record the data for frequency and the time. Then subsequently, same method for the next peak, the third peak, and the peak after. After that, we will key in the data in the Excel and then show the graph. Next, make the graph into exponent graph and show the equation. So this value will be our amplitude, and then the negative 0.493 will be our decay rate.
Our objective is to prove the system is an underdamped system and to find the natural frequency of the beam and to determine the decay rate of the beam. First, we need to find the moment of initial one moment of initial, we can find the stiffness of the beam. From the calculated data, we can get the natural frequency when we apply the certain mass. Besides that, when we obtain the stiffness of the beam, we also can find the critical damping. We need to find the critical damping so that we can obtain the damping ratio. In order to find the damping ratio, we need to plot the graph in Excel and find the general form of the decay rate graph. When we obtain the decay rate graph, we can obtain the decay rate value. From the decay rate value, we can calculate the damping. When we obtain the damping, we can manage to get the damping ratio. When we obtain the damping ratio, we can find the damping natural frequency of the beam for experimental data. From the value we obtain during experiment is the damping frequency. When we obtain damping frequency and rearrange the formula, we manage to get the natural frequency of the beam for the experimental data. The natural frequency shows the trend that when mass is increased, the natural frequency will decrease. This is fulfilling the requirement for our formula. When mass is increased, the natural frequency will decrease. There is percentage of error because there might be an error when we conducted the experiment, such as the force exerted during our decay rate data collected or Now I will explain about the percentage of error. There is an error between the experimental data and the theoretical data. This is due to the systematic error that occur during the experiment conducted. The systematic error that occur is that the beam itself is not straight and it already bent before we apply any force. Thus, it occur an error during our experiment. Okay, now we proceed to the decay rate. When we increase the mass, the decay rate will also show the increase in the value. The decay rate increase because when mass is higher, the tendency for the object to stop from oscillate is longer. Thus, it takes the longer rate for the object to stop to approaching zero.